Welcome to my channel Phi Concepts CHM. You will be seeing the sixth part of the series of semiconductor diode characteristics. Here we will see the Volt-Ampere characteristics. Volt-Ampere characteristics. In a PN junction, current I is related to voltage V by the equation I is equal to I0 into e raised to V by eta into Vt minus 1. Equation 1. Where Vt is equal to T by 11,600, which is equal to Kt by E. Current I is positive and flows from P to N side, that is the diode is forward biased. Eta is equal to 1 for germanium and eta is equal to 2 for silicon, and Vt is a volt equivalent of temperature. The form of volt-ampere characteristics described in equation 1 is shown in figure 2. This is figure 2. While figure 1 shows the ideal characteristic of PN junction diode. This is figure 1. If V is greater than Vt, the unity term in equation 1 can be neglected and the current increases exponentially with voltage except for small range near the origin. When the diode is reverse biased, mod V is several times Vt. I is equal to minus I0 because E is raised to minus V by Vt is less than 1 and the exponential term in the bracket can be neglected compared to unity. The reverse current is therefore constant independent of the applied reverse biased voltage, and I0 is called as a reverse saturation current. At the reverse biasing voltage Vz, the diode characteristics exhibit an abrupt rise in reverse current, that is this second figure here. And at this critical voltage, the diode is said to be in the breakdown region. Cut-in voltage. This figure shows forward characteristics at room temperature for germanium and silicon diodes. Figure shows there exists a cut-in, offset, breakpoint or threshold voltage V gamma below which the current is very small, that is this voltage for germanium, and this is the voltage for silicon, below which the current is very small and beyond which the current rises rapidly. V gamma is equal to 0.2 volt for germanium and 0.6 volt for silicon. That is, the offset of 0.6 minus 0.2 is equal to 0.4 volt exists. That is, a break in the silicon diode characteristic occurs at about 0.4 volts higher than that for germanium diode characteristics. So this difference is 0.4. This difference is because of the reverse saturation current in germanium, which is in microamperes, while in silicon it is in nanoamperes. Further, as eta is equal to 2 for silicon, the current increases as e raised to V by 2 Vt for the initial rise in voltage, and thereafter as e raised to V by Vt only at higher voltages, and hence causes a delay in the rise of the silicon characteristics. Logarithmic characteristic. Assuming that V is several times Vt, the unity term in the equation given below can be neglected and we have I is equal to I0 into e raised to V by eta into Vt. Rearrange the term, take I0 on the other side. Taking the log, so ln I upon I0 is equal to V upon eta Vt. 2.303 into log of I upon I0 is equal to V upon eta Vt. We can write down this log I upon I0 as log I minus log I0. Rearrange the equation, we will get 2.303 into log I is equal to 2.303 into log I0 plus V upon eta Vt. So log I is equal to log I0 plus 0.434 into V upon eta Vt. Figure shows log I against V. At low currents, the plots are linear, eta is equal to 2, and the ohmic drop is negligible here. However, at higher currents, the diode behaves like a resistor and the characteristic is no longer linear. Thank you for watching this video.